The next book I want to cover is this one, Differential Topology by Guillemin and Pollack. And it is a book on differential geometry, but not the geometry side, but only the topology. So we deal with manifolds and smooth maps, transversality and intersection, oriented intersection theory, and integration on manifolds. And then there are appendices on measure zero and Sachs theorem and classification of compact one manifolds. This book really is the Bible of differential topology. You will see it everywhere mentioned. Whenever you ask for a book on differential topology, you'll see that this book is mentioned. How does this compare with other books like Lee? I think this book does everything in terms of Rn. So everything is embedded in Euclidean space, while Lee does it in general. So if you're looking for a book that covers things on the basis of general relativity or other physics, this book might not be for you, since it wouldn't be general enough. Of course, once you know the Whitney's embedding theorem, things will be general enough, and you can just do this book. But yeah, I think it's a bit of a bad part that they really try to do everything in terms of Rn instead of in a general manifold, because I think that's probably not a good thing. But yeah, there's a lot of really interesting things in this book. Very difficult exercises as well. So if you want to go deep into differential topology, definitely give this book a try. Next, we come to the Bible, I think, of algebraic topology. It's this book by Tom Dieck, and it covers a lot of algebraic topology, very, very rigorously, very categorically. So we start with topological spaces. Everything of topological spaces he needs, he does in 20 pages, so you can see how thorough this book is. The fundamental group, covering spaces, elementary homotopy theory, co-fibrations and fibrations, homotopy groups, stable homotopy duality, cell complexes, singular homology, homological algebra, cellular homology, partitions of unity in homotopy theory, bundles, manifolds, homology of manifolds, cohomology, duality, characteristic classes, homology and homotopy, and Bordism. So yeah, it treats things very categorically. It treats things very rigorously, very abstractly too. So you really have to know your topology well to be able to handle this book. You have to know your algebraic topology well already, and of course also your category theory, because yeah, it will start using that throughout in a very rigorous way. So yeah, but yeah, it is a very good book though. It really does contain everything you need it to contain. Next, we have a book by Voigt on quantum theory, groups, and representations, an introduction. This is a book on quantum theory for mathematicians. So it starts with the group U1 and representations, two-state system, and SU2. Linear algebra review, unitary and orthogonal groups, Lie algebras and Lie algebra representations, rotation and spin groups in 3 and 4 dimensions, rotation and the spin 1/2 particle in a magnetic field, representations of SU2 and SO3, tensor products, entanglement and addition of spins, momentum and the free particle, Fourier analysis and the free particle, position and the free particle, the Heisenberg group and the Schrödinger representation, the Poisson bracket and symplectic geometry, Hamiltonian vector fields and the moment map, quadratic polynomials and the symplectic group, quantization, semi-direct products, the quantum free particle as a representation of the Euclidean group, representation of semi-direct products, central potential of the hydrogen atom, the harmonic oscillator, coherent state and a propagator of harmonic oscillator, the metaplectic representation and annihilation of creation operators, complex structures and quantization, the fermionic oscillator, Weil and Clifford algebras, Clifford algebra and geometry, anti-commuting variables and pseudo-classical mechanics, fermionic quantization and spinors, and just it goes on and on. There's like 50 chapters. The thing about this book that I've read a large part of it, and I think it's too mathematical, in the sense that everything is done rigorously, but there is no attention to the physics. I think there's very little attention on what it means physically, how to interpret things physically. It basically is just mathematics. It is just group theory, or manifold theory, or whatever it covers, just with some physical names. There's no mention of experiments. There's no mention of links with mechanics or anything. I think I was really pumped for this book. I really wanted to do this book, but in the end I didn't really find it useful. I just quit it halfway. Because I think it's like, if you want a book, quantum mechanics for mathematicians, you should do Hall's book. I think Hall is a very good quantum theory book. But I don't think this is it. If you're a mathematician interested in things related to quantum mechanics, then yes. Otherwise, if you really want to learn quantum mechanics, then I probably wouldn't recommend this book. Next, we have Gravitation and Spacetime by Ohanian and Ruffini. So we start with Newton's gravitational theory, the formalism of special relativity, the linear approximation, applications of the linear approximation, gravitational waves, Riemannian geometry, Einstein's gravitational theory, black holes and gravitational collapse, cosmology and the early universe. This book is it's an Ohanian book, so it's pretty difficult. It has pretty difficult exercises. It has a huge emphasis on experiments. Like here we have experiments on how to measure G, for example, capital G, the gravitational constant. There are many things that you find only in books like this and not really in related books. I think you got to be very comfortable with the material already if you really want to get something out of this book. Because it's very hard. The exercises are very difficult, just like any Ohanian book, really. Next we have this book, Multiple View Geometry in Computer Vision by Hartley and Zisserman. It starts with projective geometry and transformation of 2D and 3D, estimation, 2D projective transformations, algorithm evaluation, error analysis, and then it's part 1, camera geometry and single view geometry. Then we have part 2, two-view geometry. 3-view geometries is part 3. And then in part 4 we have n-view geometry. And then there are some appendices in part 5. So this is basically a book on computer vision, on basically reconstructing views, reconstructing the cores based on cameras and how cameras see things. It has some very nice links with projective geometry, so that's extremely interesting on how projective geometry is used in these things. But I have not done this book myself yet, so I can't really comment if it's good or not. Next we have this book, Thermal Physics, Thermodynamics and Statistical Mechanics for Scientists and Engineers by Sekerka. So we have part 1 on thermodynamics, so part 1 on thermodynamics, and we have the first law, we have the second law, we have the third law, we have open systems, equilibrium and thermodynamic potentials, requirements for stability, monocomponent phase equilibrium, two-phase equilibrium for van der Waals fluids, binary solutions, external force and rotating coordinate systems, chemical reactions, thermodynamics and fluid force interfaces, thermodynamics of solid fluid interfaces. Then we have statistical mechanics part, entropy and information theory, microcanonical ensemble, classical microcanonical ensemble, distinguishable particles with negligible interaction energies, canonical ensemble, classical canonical ensemble, grand canonical ensemble, entropy for any ensemble, unified treatment of ideal Fermi, Bose, and classical gases, Bose condensation, degenerate Fermi gas, quantum statistics, and the Ising model, and then some appendices. So yeah, this is basically a book on thermodynamics and statistical mechanics. A very good book, extremely good book. I really like this one. Yeah, you see that's the basic topics. The problem, I guess, with this book is that it misses problems. It misses, good problems. There are example problems which you can, I guess, work through, and then, but there's not many of them in there, I think. So, I wouldn't recommend this book to anybody, because it does have good theory, it does have good explanations, but I think the problems are very lacking and are not there. So I think that's not a good thing for a book. Then we have The Number Sense by Stanislas Dehaene. And it's basically on what exactly is a number psychologically. So it talks about our numerical heritage. It talks about beyond approximation and of neurons and numbers, and then the contemporary science of number and brain. So it really talks about what are numbers, how do we see numbers, do animals see numbers, to how much can we count naturally, stuff like that. A very interesting book on psychology of mathematics and numbers. Very recommended to anybody who's interested in this kind of psychology and maybe even philosophy. Really like this book a lot. And then we come to a book that I think Crimson might like, but I've already told him a lot about it. It's Introduction to Algebraic Geometry by Justin Smith. Extremely good book, very well written, I think. So we have classical results, where we do Bezout's theorem and the mystic hexagram theorem, affine varieties, local properties of affine varieties, varieties and schemes, projective varieties, and then chapter 6 is on curves, and then some appendices on algebra, sheaves and ring spaces, vector bundles and cohomology. I really like the way he does things in this book. I think he does it in exactly the way I would do it too. There are various numbers of very good exercises, I think. If you already know algebraic geometry from, say, a book like Garrity or Cox, this is excellent. This is exactly, I think, the follow-up book that you might want. There are other follow-up books, like Ueno is also a very good follow-up book, but this is also a pretty good one. And I think one I really do like a lot. And it does go quite far. It goes all the way until schemes and tells you the basic of schemes. I think I wish I had this book when I was doing my PhD thesis, but I don't think it's that old, that book. So very good book, highly recommended to Crimson and anybody interested in see how extensive the appendices are. They're just like 1/3 of the book, so that's excellent too.